continuing the feature selection, we have been discussing so far the algorithms like sequential forward, sequential backward, generalized sequential forward, generalized sequential backward, LR algorithm and branch and bound algorithm. There are many other algorithms available. So, now I will start discussing the feature selection criterion functions, how to choose the choice of the feature selection criterion functions. So, again, so there are x 1 to x n, you have totally n variables or capital N number of features, and so your feature vector is going to be of, if I write the feature vector as for the ith observation, if I write the feature vector, then this is for the ith observation, the value of the first feature is x 1 I, for the ith observation the value of the second feature is x 2 I, for the ith observation the value of the nth feature is x n I. So, it is your feature vector will be in capital N dimensions. Okay. Now, let us just say that there are how many classes? Let us just say there are k number of classes, the number of classes is k. The number of classes is k, and let us assume that we know the class conditional density functions, that is for the first class it will be small p 1, for the second class it will be small p 2, for the ith class it will be small p k. So, they are k class conditional density functions, probability density functions, and let us just say there are the corresponding prior probabilities p 1, p 2 up to p k. Naturally, each of them is greater than 0 and then the summation is actually equal to 1. Let us just say we know this, we know these things and as well as we know this. Now, we are supposed to select small b number of features, small b number of features they have to be selected. So, let us just consider one such subset. Let us just say capital B is a subset of S, let B is a subset of S and B contains small b features. Okay. Let us say B is a capital B is a subset of S such that capital B contains small b number of features. Now, with respect to those small b number of features, we can have the density function p 1 b, p 2 b, p k b. Using those features in this subset capital B, the corresponding conditional probability density function for the class 1 is small p 1 b. Do you know how to get this small p 1 b from this small p 1? Do you know it? If you do not know it, please tell me. How you will get is, you see the small p 1 is going to be here these integrations are how many such integrations? Capital N number of such integrations. small p 1 of this, you know, because since small p 1 is a density function and its number of arguments is capital N. So, you have to write those capital N variables x 1 to x n and dx 1 dx 2 dx n, and these number of integrations is you are going to integrate over capital N dimensional space. Okay. Maybe each of them is R. Okay. R this is equal to 1. Okay. Integration over capital R to the power n, right. Now, you look at those B features here. Let us say without loss of generality, this, let us say this subset B is equal to, let us just say x 1 to x B. These are the B features that we have taken. Let us just say, then what we will do is that look at this function p 1 of x 1 x 2 x b plus 1 x b plus 2 x n. Okay. This I will do the integration over dx this I will do the integration. So, this will be how many n minus b over n minus b dimensional space, or basically this is same as integral r to the power of n minus b p 1 So, if you do the integration, what are you going to get? Let us just say the function that you are going to get, let me just write it as g, and for the class 1 let me just write it as g 1. Actually here I wrote p 1 b. So, let me just write it like this only, p 1 for the set B. What are these arguments? Because x 1 to x b they are there, you are doing the integration over b plus 1, b plus 2, etc. Are you understanding? You are doing the integration over b plus 1, b plus 2, etc. b up to capital N. So, there are some variables which are there remaining there. What are the variables that are remaining? X 1 to x b, they are this in capital B you have these features. So, that is your p 1 b. Have you understood what I wanted to say? Similarly, you can have p 2 b, p 3 b, p k b. And that you can have it for any such subset of S. It may have small b number of elements, it may have, I mean this capital B can be any subset of S having small b number of elements. Which are those small b features that you can vary? By varying capital B, you can get the corresponding these sets, these density functions. These are actually called marginal density functions. You are doing the integration with respect to the rest of the variables, so that the variables that you want, they will just remain as they are. Okay. So, once you get this P 1 b, P 2 b, P k b, then what you can do is, you can use these prior probabilities and you can get the base decision boundary and you can get the base misclassification probability. So, find the misclassification probability of the base decision rule using these B features, using the features in B. And denote the misclassification probability as, and denote the misclassification probability as J B. Is this clear? Denote the misclassification probability as J B. Now, you are supposed to do the feature selection. So, now what is your criterion function? Your criterion function is, I mean this J, and you are supposed to find that particular subset B naught containing small b number of elements for which J of B naught is minimum. That is, find B naught subset of S B naught containing B elements such that symbol is this, J of B naught is less than or equal to J of B. For all B subset of S containing small b number of elements. Is this clear to you? This should be the way in which feature selection should have been done, but usually people do not go in for this. What is the reason? The reason is very simple. For most of the problems, you really do not know the probability density functions. For most of the problems, you really do not know the probability density functions. That is one part of it. But the second part, even if you know, it is difficult to calculate J of B. It is difficult to calculate the misclassification probabilities. If you look at my earlier lectures on base decision rule, which was supposed to be the best rule, then why at all we went in for other decision rules? The reason was that even if you know the probability density functions, it is extremely difficult for you to find the misclassification probabilities, to find which one is actually the minimum. It is difficult to get those decision rules and the corresponding misclassification probabilities. It is difficult to get the misclassification probabilities. So, this should have been the rule that people should have followed it, but actually it is difficult to follow it, because you really do not know how to, though the expression is fine, but it is difficult to evaluate the expression for misclassification probabilities. Then people started wondering, is there any way in which one can actually choose features using probability density functions, but without actually going in for calculating base misclassification probabilities. How to look at density functions without really trying to calculate the misclassification probabilities. This was the question people asked themselves, and then they came out with the probabilistic separability based criterion functions. Now, what is the meaning of probabilistic separability based criterion functions? In order to explain probabilistic separability based criterion functions, I will explain the things in this following way. Say these are two density functions for the classes. Say this is the density function for the class 1, say this is the density function for the class 2, right, and then note that there is a gap here. Okay. Note that there is a gap here. So, these two functions, they satisfy a property. What is the property? P1x greater than 0 implies P2x is equal to 0. P1 of this thing is greater than 0. What about P2 for these points? That is equal to 0. Similarly, okay. Now, suppose we have chosen the required number of features in such a way that those features, they separate out the density functions like this. Then what is going to happen to the Bayes decision rule in this case? If your density functions P 1 and P 2 are like this, what will happen to your Bayes decision rule? Does it give you any misclassification? Yes or no? My claim is that there is no misclassification. Why? What is the Bayes decision rule? Bayes decision rule is put x in class 1 if P1 x is greater than P2 x. This is in the case of two classes. Now, here when P1 x is greater than 0, P2 x is 0. So, for all the points which are here, they will go to class 1. and for all the points which are in this region they will go to class 2, because p 2 p 2 x will be greater than 0, but p 1 p 1 x is equal to 0. So, then there is no misclassification, right, then there is no misclassification. So, what people thought was that they would like to choose features in such a way that the density function, the separation between the density functions is as much as possible. The separation between the density functions is as much as possible. That is the basic idea. That is why it is called separability, that means separation between the density functions. Since we are looking at density functions, people called it as probabilistic separability. Have you understood it now? So, this is called as probabilistic separability based feature selection criterion functions. Now, the question is, how do you define the separation between two density functions? If you define that, then you can talk about which features are going to give you the maximum separation. Are you understanding what I am trying to say? If you somehow define the separation between the density functions, then we can say which particular features give you the maximum separation. So, how does one define the separation between the density functions? Let us see. So, you have say two classes. So, you have density functions p 1 and p 2, you have prior probabilities p 1 and p 2. Okay. Now, you need to define a function which you need to define some g, some sort of integration may be done, okay. And then you need to have, let us just say you need to define some g 1 and then again you need to define a g 2. So, this is a general way in which you can define separation between density functions. You need to have some g 1 here and then some g 2, but then it should have some properties. What are the properties? The properties are 1, J is maximum if p 1 x greater than 0 implies p 2 x is equal to 0. That maximum value for some functions it may be of the order of 1, for some functions it may be infinity. By varying this g 1 and g 2, you may get several such maximum values. I mean, people defined it in just too many ways. Okay. 2, J is minimum if If P 1 x is equal to P 2 x for all x, then there is no separation between the density functions. Am I right? Then you should have a minimum value. Are you understanding? First I am trying to give you the intuition, now I will give you the formulas. It should be maximum when P 1 x greater than 0 implies P 2 x is equal to 0. Okay. Minimum when P 1 x is equal to P 2 x for all x. I am expecting a question from you. Okay, let me ask you that question. Here I wrote only one, P 1 x greater than 0 implies P 2 x is equal to 0. Do I need to write the other one? P 2 x greater than 0 implies P 1 x is equal to 0. What is the other one? Do I need to write it? I claim that I do not need to write it. I will tell you why I do not need to write it. Suppose this is not true, that means there is one x for which P 2 x is greater than 0 as well as P 1 x is also greater than 0, but that does not happen. Okay. If there is an x for which both P 1 and P 2 are greater than 0, then it contradicts the previous statement. Are you understanding? Have you understood the logic? So, I do not need to write this, just this one statement is sufficient. Is it clear to you? And the third one is that, so I wrote maximum and minimum, and all the other cases they should be in between this maximum and minimum. For all other cases, J lies between the maximum, the minimum and maximum. This minimum is same as this minimum, and this maximum is same as this maximum. Okay. So, using these principles, several criterion functions have been defined. Several criterion functions means several separability measures have been defined, and using those separability measures you can have the corresponding criterion functions for feature selection. Okay. Now, what are those separability measures which tell you how to look at the, how to quantify the separation between the density functions. Okay. The first one I am going to give, this will be by Bhattacharya. Okay. This is integral This is by Bhattacharya. This log is to the base e. Okay. It looks to be quite complicated, but actually it is not. Let us look at the case 2, that is the second one. Suppose p 1 x is equal to p 2 x, then what is going to happen to this one? This is integral p 1 x, and you are going to do the integration over the whole space. So, this value is going to be 1, log 1 is equal to 0 and minus of 0 is 0. So, the minimum value is 0. Now, let us look at the other one. What will happen to this product? The product is 0, square root is 0, integral of 0 is 0, and log of this thing it is minus infinity. Actually, log 0 is not defined. When something that is going towards 0, then this goes towards minus infinity, and minus of log is plus infinity. Have you understood? Now, have you understood why such an expression is taken? Is it clear? And you know who this Bhattacharya is? He was a professor in Calcutta University. As I was mentioning in one of my discussions with you, ISI was created by Mahalanobis in the Calcutta University way back in 1931. Okay. He started ISI in 1931 in Calcutta University. There has always been a close interaction between the scientists of Indian Statistical Institute and Calcutta University. Okay. And Bhattacharya, he was a professor in Calcutta University. I think he died around 8 to 10 years ago. He never went abroad. He never went abroad, and a very famous scientist, and this distance is known as Bhattacharya distance. Probably you might have heard the term Bhattacharya distance. So, this is the one. Bhattacharya distance is this. Okay. He was a very famous statistician, and he actually developed this one, Bhattacharya distance. And this was generalized by Chernoff. So, how did he do it? As you can see here, if you put S is equal to half, you will get Bhattacharya distance, right. So, he had this was generalized, he took any S lying between 0 and 1. So, then you will get a generalization. And Matsushita, there is Matsushita there. How did he do it? This is integral square root p 1 x minus square root p 2 x whole square dx. Okay. And there are in fact many more. There is something called divergence, and there are many more such measures. Each of them uses the density functions. Okay. Using these separability measures between the density functions, one can always define the corresponding criterion functions for feature selection. For example, how do you define a criterion function using this Bhattacharya distance? How will you define it? You say that you take those small b features for which the Bhattacharya distance value is maximum. Okay. You take those small b features for which the Bhattacharya distance is maximum. So, for each such set you will get the corresponding what I wrote there p 1 b, p 2 b I wrote when I explained it to you. You will get the corresponding p 1 b and p 2 b, and then you calculate the Bhattacharya distance. So, for every such set B containing small b number of elements, you have the corresponding Bhattacharya distance value, and you find out that B naught for which the distance is maximum, the separation is maximum. Okay. Similarly, using Chernoff or using Matsushita, or I mean looking at there are many other measures, you will get the definitions of these things from DeWeber and Kitter's book. You can get, there are in fact too many of them. He goes on giving the corresponding formulas for those measures, right. Now, note that in these cases I assume that you have two classes, but supposing you have k number of classes, instead of two classes, suppose you have k classes, that means p 1, p 2, p k, and here you have capital 1, capital P 2, capital P k. Now, how are you going to get the separation between k such density functions? How do you get the separation between the k such density functions? We will look at what is known as the mixture density function p x. Let us just define it as this is mixture density function, that is one terminology for this, and you also have another terminology for this. This is actually the mean of these I density, these k density functions, is not it the mean of these k density functions? These are the probabilities, multiply the function by the probability, take the summation, you will get the mean. And we are supposed to look at separation between any two such density functions, and whatever I did earlier, that you do not need to look at the separation between any two such things, you always look at the separation of that function with respect to the mean and take the summation, that will give you the separation between any two of them and take the summation. Have you understood what I wanted to say? What I did about the variance, you are looking at the difference between the mean and each individual value, taking the square and then doing the summation, whereas we are supposed to look at the separation between any two of them and take the square and look at the summation. Here the problem is we are supposed to look at the separation between any two of them and then take the summation to get the overall value. So, instead of looking at that, we can always look at the mean and take the difference separation between each of them with respect to the mean, and you sum it up. Have you understood what I wanted to say? So, you can have the corresponding generalization of these things, not with respect to two density functions, but the generalization with respect to m density with k density functions. So, what is the generalization? The generalization is for Bhattacharya, it is going to be minus log integral square root p I x, and this is p x dx. This you multiply it by p I and you take the summation I is equal to 1 to k. You take the summation I is equal to 1 to k p I bracket and you write it with respect to p I and p. Have you understood this? This is just the generalization of Bhattacharya distance, but not for two classes, but for k classes, taking it from the for the two classes whatever may be the formula, that formula is generalized for k classes here, and you can have the corresponding generalizations for Chernoff and also for Matsushita and for other such measures, other such separability measures. And there are simply many of them in the literature. There are simply many of them in the literature. Since the earlier part of the literature, it was for feature selection, people wanted to directly use the statistical principles. So, there are several such papers using these distance measures, which you would find in the early part of the literature on feature selection. This is denoted as probabilistic dependence measures. This is the terminology that was used by DeViver and Kittler in their book. They called it as probabilistic dependence measures for feature selection, which are nothing but generalization of the probabilistic separability measures to k classes. Simply the generalization of the probabilistic separability measures to k classes. Do you have any questions? In my next lecture, I will start dealing with when the density functions are not available, you have a training sample set. Then how do you do how do you get the criterion functions for feature selection? Here in all these cases, I assumed that the density functions are available. So, we try to develop the criterion functions for feature selection. Now, in my next lecture, I shall deal with the case where the density functions are not available, but a training sample set is available for feature selection, and so then how do you get the criterion functions in that case? It is over.